For this application, using number 2 XLP in a 4-inch conduit is a viable plan. Table 310.77 applies to 3 conductors in a raceway. Ethylene-propylene rubber is a popular insulation material. Cross-linked polyethylene is more expensive but offers superior insulation properties. Installing all 3 conductors in one conduit is acceptable. If using metal conduit, ensure the feeders aren't used as a ground path by bonding them to the equipment at both ends. Failure to bond the feeders could overload them in the event of a ground fault. Alternatively, you can install 3 separate conduits, which would necessitate increasing the spacing between them, as the fill of each conduit would be less than 40%. The calculation for the primary overcurrent protection involves dividing the apparent power of the transformer, which is 2500 kVA, by the primary voltage of 12 kilovolts, and then dividing again by the square root of 3, which accounts for the 3-phase nature of the system. Finally, multiply the result by a safety factor of 1.25, which is common practice to account for continuous loads or other factors that might increase the current draw. This calculation yields the required primary overcurrent protection in amps. The selection of number 2 copper XLP cable is based on its ampacity, or current carrying capacity, as listed in Table 310.77 of the National Electrical Code, or NEC. This table provides ampacity values for various conductor sizes and insulation types based on different installation conditions, such as direct burial or installation in a raceway. The note referencing 133% relates to the overcurrent protection of transformer primary conductors, as outlined in NEC section 450.3. This section permits the overcurrent protection device to be sized at up to 125% or 250% of the transformer's rated primary current, depending on specific conditions and the type of overcurrent device used, such as a circuit breaker or fuses. The provided software cut sheet indicates that number 2 XLP cable has an approximate diameter of 1 inch, which translates to 0.79 square inches of cross-sectional area. When installing 3 such cables in a single conduit, the total cross-sectional area occupied by the cables is 3 times 0.79 square inches, or 2.37 square inches. The NEC specifies maximum conduit fill percentages to ensure proper heat dissipation and ease of installation. For 3 or more conductors, the maximum allowable fill is typically 40%. To determine the appropriate conduit size, calculate the required conduit area by dividing the total cable area by the allowable fill percentage. In this case, 2.37 square inches divided by 0.40 yields a required conduit area of 5.925 square inches. Based on standard conduit sizes, a 4-inch conduit provides an area of approximately 12.7 square inches, which is sufficient to accommodate the 3 number 2 XLP cables with a 40% fill. Installing 1 cable in each of 3 conduits is an alternative approach. When using metal conduit, bonding is essential to ensure a low impedance ground fault path. Bonding involves connecting the metal conduit to the equipment grounding system at both ends, which allows fault current to flow back to the source and trip the overcurrent protection device. Without proper bonding, the metal conduit could become energized during a ground fault, posing a safety hazard. The choice between cross-linked polyethylene and ethylene-propylene rubber insulation depends on factors such as operating temperature, environmental conditions, and cost considerations. Cross-linked polyethylene generally offers better resistance to moisture and chemicals, while ethylene-propylene rubber provides greater flexibility and elasticity. Shielding is used to contain the electric field surrounding a high-voltage cable and to protect the cable from external interference. Tape shields consist of a thin layer of metallic tape wrapped around the insulation, while wire shields are made up of multiple strands of wire. Wire shields typically offer better shielding performance and are more robust than tape shields, but they may also be more expensive. When installing conductors in conduit, jamming can be a concern, especially when using multiple conductors or conductors with large diameters. To minimize the risk of jamming, use proper pulling techniques, such as lubricating the conductors and using pulling elbows to reduce bending stress. Additionally, consider using larger conduit sizes or installing the conductors in separate conduits to provide more space and reduce friction. The 12 kV feeder is supplying power to a 2500 kVA transformer. The primary current calculation involves dividing the transformer's KVA rating by the primary voltage and the square root of 3, then multiplying by a safety factor. The NEC guidelines dictate the appropriate ampacity for the number 2 copper XLP cable, referencing table 310.77 for conductors and raceways. Determining whether the loop is grounded is crucial for applying the correct ampacity adjustment factors. The self-wire cut sheet specifies the cable's diameter, which is essential for calculating conduit fill. Conduit fill calculations ensure compliance with NEC standards, typically limiting fill to 40% for multiple conductors. The option of using separate conduits versus a single conduit is weighed, considering factors like heat dissipation and ease of installation. Metal conduit requires proper bonding to ensure a reliable ground fault path, while the choice between cross-linked polyethylene and ethylene propylene rubber insulation depends on performance and cost considerations. Tape and wire shields offer different levels of protection against electrical interference. Jamming during cable installation can be mitigated by proper techniques and conduit sizing. The formula for calculating the primary current is as follows. Primary current equals transformer KVA divided by primary voltage divided by the square root of 3, then multiply by 1.25. So, primary current equals 2500 kVA divided by 12 kV divided by the square root of 3, then multiply by 1.25. Understanding NEC table 310.77 is important because it specifies ampacities for conductors based on insulation type, size, and installation method. The table provides ampacity values for conductors in various conditions, such as free air, raceways, and direct burial. Factors like ambient temperature and the number of current-carrying conductors in a raceway can affect the ampacity of the conductors. The 133% adjustment factor likely refers to the overcurrent protection requirements for transformers, as outlined in NEC section 450.3. This section permits the overcurrent protection device to be sized at up to 125% or 250% of the transformer's rated primary current, depending on specific conditions and the type of overcurrent device used, such as a circuit breaker or fuses. Confirming whether the loop is grounded is crucial because it can affect the selection of grounding methods and equipment. Grounded systems require different grounding practices compared to ungrounded systems. In grounded systems, the neutral point is intentionally connected to ground, which provides a reference point for voltage and helps to limit voltage surges. Ungrounded systems do not have a direct connection to ground, which can result in higher voltage stresses on equipment and a greater risk of transient overvoltages. The dimensions provided in the self-wire cut sheet, specifically the diameter of the cable, are used to calculate the cross-sectional area of the cable. This information is necessary for determining the appropriate conduit size based on conduit fill requirements. Conduit fill calculations ensure that the conductors are not overcrowded in the conduit, which can lead to overheating and insulation damage. The NEC specifies maximum conduit fill percentages based on the number of conductors in the conduit. For example, for 3 or more conductors, the maximum allowable fill is typically 40%. The choice between installing all 3 conductors in one conduit versus using separate conduits depends on factors such as cost, space constraints, and heat dissipation requirements. Installing all conductors in one conduit is generally more cost-effective and requires less space, but it can also result in higher conductor temperatures due to reduced heat dissipation. Using separate conduits can improve heat dissipation and reduce conductor temperatures, but it may also be more expensive and require more space. When using metal conduit, bonding is essential to ensure a low impedance ground fault path. Bonding involves connecting the metal conduit to the equipment grounding system at both ends, which allows fault current to flow back to the source and trip the overcurrent protection device. Without proper bonding, the metal conduit could become energized during a ground fault, posing a safety hazard. Ethylene propylene rubber and cross-linked polyethylene are common insulation materials used for high-voltage cables. Ethylene propylene rubber is a synthetic rubber insulation material that offers good flexibility, elasticity, and resistance to moisture and chemicals. Cross-linked polyethylene is a thermoplastic insulation material that offers excellent electrical properties, high temperature resistance, and resistance to abrasion and chemicals. The choice between tape and wire shields depends on factors such as shielding performance, flexibility, and cost. Tape shields consist of a thin layer of metallic tape wrapped around the insulation, while wire shields are made up of multiple strands of wire. Wire shields typically offer better shielding performance and are more robust than tape shields, but they may also be more expensive. Damming during cable installation can occur when the conductors become stuck or entangled in the conduit. To minimize the risk of jamming, use proper pulling techniques such as lubricating the conductors and using pulling elbows to reduce bending stress. Additionally, consider using larger conduit sizes or installing the conductors in separate conduits to provide more space and reduce friction. The NEC provides guidelines for selecting the appropriate size and type of conduit for electrical installations. These guidelines take into account factors such as the number and size of conductors, the type of insulation, the installation environment, and the required ampacity. Selecting the proper conduit size is essential for ensuring that the conductors are adequately protected and that the installation complies with safety standards. The NEC specifies requirements for grounding electrical systems to ensure safety and prevent electrical shock hazards. Grounding involves connecting the non-current carrying metal parts of electrical equipment to ground, which provides a low impedance path for fault current to flow back to the source. Proper grounding is essential for minimizing the risk of electrical shock and for ensuring that overcurrent protection devices trip quickly in the event of a fault. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The ampacity of a conductor depends on factors such as the size and type of conductor, the insulation material, the installation environment, and the number of current-carrying conductors in a raceway. The NEC provides tables and guidelines for determining the ampacity of conductors under various conditions. The overcurrent protection device, such as a circuit breaker or fuse, is designed to protect electrical circuits and equipment from overloads and short circuits. The overcurrent protection device is sized to trip or open the circuit when the current exceeds a predetermined level. Proper sizing of the overcurrent protection device is essential for preventing damage to equipment and for ensuring safety. The voltage drop in an electrical circuit is the decrease in voltage from the source to the load. Voltage drop can occur due to the resistance of the conductors and the impedance of the circuit. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC provides guidelines for limiting voltage drop in electrical circuits. The short circuit current is the amount of current that flows in a circuit during a short circuit. The short circuit current can be very high, and it can cause significant damage to equipment and create a safety hazard. It is important to calculate the short circuit current for electrical systems to ensure that the overcurrent protection devices are properly sized and that the equipment is adequately protected. Harmonics are distortions in the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause problems such as overheating of equipment, increased energy losses, and interference with communication systems. It is important to mitigate harmonics in electrical systems to ensure efficient and reliable operation. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is not being used to do useful work. A low power factor can cause increased energy losses, reduced equipment capacity, and increased utility costs. It is important to improve power factor in electrical systems to reduce energy losses and improve efficiency. Surge protection devices are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, and other disturbances. Surge protection devices divert the surge current to ground, protecting the equipment from damage. It is important to install surge protection devices in electrical systems to protect sensitive equipment from voltage surges. Electrical safety is of utmost importance in all electrical work. It is essential to follow safe work practices, use appropriate personal protective equipment, and comply with all applicable codes and standards. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent electrical shock and other hazards. Proper planning and design are essential for ensuring the safety and reliability of electrical systems. This includes selecting the appropriate equipment, sizing conductors and overcurrent protection devices, and providing adequate grounding and bonding. A well-designed electrical system will minimize the risk of electrical hazards and ensure efficient and reliable operation. Regular maintenance and testing are essential for ensuring the continued safety and reliability of electrical systems. This includes inspecting equipment for damage, testing overcurrent protection devices, and measuring voltage and current levels. Regular maintenance and testing can help to identify potential problems before they become serious and can prevent costly downtime. Adhering to the NEC is crucial for ensuring the safety and compliance of electrical installations. The NEC provides comprehensive guidelines for all aspects of electrical work, from wiring methods to grounding and bonding requirements. Compliance with the NEC is essential for protecting people and property from electrical hazards. Continuous learning and professional development are essential for staying up to date with the latest advancements in electrical technology and for maintaining competency in electrical work. This includes attending training courses, reading technical publications, and participating in professional organizations. Continuous learning is essential for providing high-quality electrical services and for ensuring the safety of electrical installations.